Okay, we're going to take a look at an additional rule for integration referred to as integration by parts. And this method of integration by parts is derived directly from the product rule for differentiation. And sometimes you'll see the notation u and v for the two variables, or f and g, and we've been using f and g earlier on. So use whichever you prefer. I think in the following development I'm going to use U and V. So we'll be following this notation up here. And before proceeding, I'd ask you to evaluate the integral of these differentials. You use whichever whichever notation you prefer, and evaluate or determine what the integral of this relationship is going to look like. Take a minute to do that. And if you did that, really what we're doing here is we're just integrating the differential uv. That's going to give us uv down here. And then we'll have the integral u dv plus the integral v du. Now, we assume that we have a problem that would be an integral like this, could be this, doesn't matter, but using the integral u dv, we shift these terms around, and we say that the integral u dv in this case is going to be equal to uv minus the integral v du. So the basic integration by parts, we have to take an integral which we have been unable to solve and break it down into, assign it what's going to be u, what's going to be dv, and evaluate v du, and so on. So this does turn out to be a powerful technique to help you solve more complex integrals. And let's take a look at this. Let's take a look at an example. Now, let's say you have an integral like this, x e to the x dx, and you've tried integration by substitution. You've tried to, let's say we let x equal u, then dx is equal to 1. That doesn't really help us. If u is equal to e to the x, du dx is just equal to e to the x. We can't get x out of that if we assume this as our variable of substitution. We can't get e to the x out of this. We can't get x out of this if we assume this is our variable of substitution. So, try as you may, you're going to have a difficult time trying to integrate this by the techniques that we've already learned. So we know, though, that this integrand, it's a derivative of something, but we just, at least I can't figure out what that something is. So we look at this integral as containing two basic parts, a u and a dv. So u and a dv, and we have to make those assignments. So taking a look at this integral, I'd ask you to take a minute, pause the video. What would you define as u, and what would you define as your dv? There are several possibilities here. So u could be equal to x, or u could be equal to e to the x, and dv would be equal to dx, or the derivative of e to the x dx would be dx. So take a minute and pick your u and your dv. And let's say you picked u equal to x and dv equal e to the x dx. So at this point, well, we have to say, okay, what's du? Well, du is just dx. So we have dx here. And then we have to determine what v is here. So v is going to be we have a dv, so we have to take the integral of e to the x dx. And of course, this is that simple integral we found that, if we integrate this, we always get this back. We can integrate it as many times as we want. We always get e to the x. I'm kind of leaving out the constants here. They do belong in here, but just developing the basic idea. So we have the terms that we need, and when we substitute those in, we get this original integral x e to the x dx is equal to x e to the x minus the integral e to the x dx. Well, this looks a little bit more manageable if we continue through with this evaluation, just kind of substituting this back in here. We get the integral x e to the x dx is equal to x e to the x minus the integral of e to the x dx, which we know is minus e to the x. And we can undistribute our e to the x and factor it out, and so that we get e to the x times x minus 1. So we've evaluated this integral, and I think this solution would have been a little bit difficult to see using any other technique, but it falls out very nicely using integration by parts. So here's another example. Let's say that you let u, or this is the same example, but another choice of u and dv. Let's say you had started off, you say, well, okay, I want to let u equal e to the x and dv equal x dx. Okay. So based on this, we would have that du, the derivative of u with respect to x, or du would be e to the x dx. V would be the integral of x dx, which would be 1/2 x squared. And then if we substitute that all back into this expression over here, we have the integral x e to the x dx is equal to x squared. It's our 1/2 x squared here times v, which is, or times u, which is e to the x. Okay, kind of just reverse their order here, so we have x squared e to the x over 2 minus the integral of 1/2 x squared e to the x dx. So that really didn't help us. So we did have another choice here. If you'd have taken this road, you would have ended up with another integral that would have been, well, you could say, well, okay, I'll try the differentiation by parts again, or integration by parts again. So you usually do have multiple guesses, and if one doesn't work out, then you can use another one. So let's try another example here. We have x squared sine x dx, and I'd ask you again just to take a moment and figure out what your u and dv assignments are going to be. So you can pause and do that. And if we let u equal x squared and dv equal sine x dx, then we have that v is going to be the integral of sine x dx, which is going to be minus cosine x, and du will be equal to 2x dx. So that, if we substitute back into this relationship over here, we get minus x squared cosine x plus 2x cosine x dx. Well, we aren't home yet. We don't have a solution. We've got another integral. Is this a problem where we could have changed our assignments? Well, I'd ask you to go ahead and pick the pick the alternate set of assignments. Let u equal sine of x, dv equal x squared dx, du equal cosine x dx, and v equal x cubed over 3, and see what you come up with. Take a moment. And, if you did that, then you're going to see that you get, well, something even more complicated. X cubed over 3 sine x minus x cubed over 3, the integral of x cubed over 3 cosine x dx. That didn't help. So this option was not a good option. We're back to this solution that we originally obtained, and we're looking at this part and we're saying, okay, well, I'm going to do integration by parts again. So just evaluate this term here. So again, you designate u, dv. So we have u equal x. du is equal to dx. dv, in this expression, we're going to let equal to cosine x dx. So that v, which would be the integral of cosine x dx, would be the sine of x. And so we have x cosine of x dx is equal to x sine of x minus the integral of sine of x dx. All this we can figure out. So this integral we can evaluate using integration by parts. This works out quite well. So we go back to our original result right here. And we integrate this for this second integral into this expression. So we see that the integral x squared sine x dx is equal to minus x squared cosine x plus 2x sine x plus 2 cosine x. So we're just distributing the 2 through this solution that we have up here, which we see over here in front of the integral. So in the end then we can factor out a cosine x, and we have 2 minus x squared cosine x plus 2x sine x as the integral of x squared sine x dx. Okay, one last example. Let's take something simple like the integral of the log of x dx. Now, you may look at this and say, well, gee, I should know that. I mean, well, think about what we learned. We learned that the derivative of the log of x with respect to x is equal to 1 over x. And we learned that the integral of 1 over x, or x to the minus 1 power, is equal to the log of x. But that doesn't really help us over here. We haven't really talked about what the integral of the log of x dx would be. So again, take a look and let u equal to, you say, well, we don't really have enough up here in order to get a u in it. We don't have a u in it. Well, we do. U is equal to just let u equal to the log of x and dv equal to dx. That's going to give us a v of, if we integrate dx, we're going to get x. And that's going to give us a du. If we take the derivative of the log of x with respect to x, we're going to get x to the minus 1 dx. We plug all that back into this relationship here. We get x log of x minus the integral of x over x dx. And that reduces to x log of x minus x is equal to x, factoring out the x, times the log of x minus 1. So integration by parts is a powerful tool, and these are just a few simple examples to illustrate that. You can, and you probably are, using Wolfram Alpha to help you out with a lot of these problems. Wolfram Alpha obviously is an excellent resource that can help you check and develop your math skills. But you will benefit greatly by being able to use Wolfram Alpha as a check and to be able to better understand how you get from point A to point B in developing these solutions. So you're going to develop a much greater capability by trying to do these things on your own. So anyway, we'll probably get into some some geological, geophysical examples of integration problems in the next video. See you then.